Headers. Great. So welcome everyone. This is the second showing of our CodeJam workshop for today. What we're going to be talking about is computer vision and machine learning in industry. And the idea is to give you kind of a broader perspective of, what vision looks like in an industrial setting, and kind of show you off a bit of our tools and kind of the strategies we use to actually make things work from an industry perspective. So who are we? Well, we're from Matrox Imaging. My name is Dirk Dubois. I have a master's in engineering from the University of McGill. I also did my bachelor's in electrical engineering at McGill. And I design software for machine vision for a living. And my co-presenter with us.
Yeah, and I'm Bena. I develop machine vision solutions. So basically, once companies need the solutions to be developed using our tools, I'm working on them, provide them the solution.
So, well, Matrox is actually a pretty big company and has two main divisions. So there's the video division, which we're not from, but we'll tell you a bit about. And they fundamentally make hardware and software to do things like display walls. So you have like these big walls with all these different screens on them, and you want to be able to, split the pictures up over that. Or you want to do something like we're doing right now, where you want to stream this video live to platforms like YouTube, Facebook, etc. You want to do broadcast. So they make hardware and software for broadcast and media streaming. But we're from the imaging division, so let's talk a bit more about that instead. So what does the imaging division do? Well, we make everything that is hardware and software for machine vision. So if you have something you want to do with images, we provide all the hardware and software to allow you to do that. And we've been around for a really long time, for about 40 plus years. We're a Montreal-based company. We're located in Dorval. And all the engineering work is done here in Montreal. So from the design, the development, to the testing, to even some of the manufacturing, we have our own assembly line. We manufacture stuff right here in Montreal. So what is machine vision? I think that's important to understand. So machine vision helps you automate inspection. So you have an image of something, and you want to detect something in that image, like you want to detect objects or parts in an image. Or maybe you want to measure something in that image. Once you've found that part, you actually want to be able to measure it, see if it's the right tolerance, see if it's the right size. And customers do that with this library we provide, the Matrox Imaging Library, or MIL. You'll hear us talk about MIL a lot. It's an API for machine vision. So it's a software development kit you install on your PC as a developer, and you code with, you program with it. And it provides you a whole massive toolbox of functionality to do everything and anything you could possibly want to do with machine vision. So who are our customers? Well, our customers are developers that are in industrial settings, and they often have tough demands. So one of them is long-term compatibility. Unlike a hackathon where you might quickly whip something up in 48 hours and then never use it again, our customers have projects that have really long-term timelines, 5 years, 10 years, 15 years. And so long-term compatibility is really critical for them. They need really accurate results. As we'll show, since they're doing inspection, they want the results to be correct, because every time they miss something, that's, a part wasted, money lost, time loss, right? So accurate results are important. And they have real-time constraints. Oftentimes, we're talking about factories, parts moving down conveyors, robots in the loop, that sort of thing. So there are real-time constraints for them in those instances.
Yeah, so
yes, let me hit play.
Here, I'm going to present you some examples of where our tools were deployed in the industry. So what you see here is actually the wire bonding. The robot is looking at the circuits, and it locates where to start wiring and where to end the wiring. How they do it, they use our module, one of our modules called pattern matching. And what it means is you define a pattern in one image, and then once the camera on the robot is looking at the circuits, it grabs images, and in the new images you can go and search those patterns, so you can locate that part, and you fixture, for example, to find the exactly start point of the wiring. It gives you sub-pixel accuracy, so it gives you pretty robust and accurate result for the starting point and the end point. Another example is once we use deep learning in food industry. The images that you are seeing here, what we want to do, we want to classify if there is what we are looking at, it's a good muscle or a bad muscle. So the image is captured by the X-ray camera, And if there is a shell on top of the muscle, you see the black dot and the black spot on top of the muscle, the ones that you see that there is a red box around that. So those have a shell on top. That's why we see the black spot. So first we capture the images, and then since we have the images of white background and dark objects, we can easily use blob analysis, locate the objects, and then we could extract these images. And because the pattern is a bit complex, we use deep learning to train a model and then learn how to predict and classify the images into good and bad, and use that for prediction during the deployment. So here we are showing you how to actually how we can train one context in meal to be able to predict good and bad. But before that, sorry, I forgot that for this case, we have reached the accuracy of 98.6 for the context that we have trained, and it was able to predict one box that you're seeing here for a millisecond. So on the CPU, so it's pretty fast, and you can deploy it on the real-time industry. So here we show you how to. I'm waiting for the loading, but we show you how to do the training using the images. This is the second one.
There, this one.
Yeah. So
that's the one you
basically,
want. There we go.
First you need the data set. We have captured a lot of images, and what you see is actually our data set of our training set. The labels are under the images, the green boxes and red boxes, so it's pre-labeled. And you can see that some images are darker, some brighter, the noise is added. So we augmented images to have more images, and definitely it helps us to make the context more robust. And we could also generalize better. So here you are seeing some examples of the muscles that the dark spot exists, so it's a bad one or a good one. Next, you need to choose the context that you want to train. Then you have some parameters to choose. The default for us is good, but here on my GPU is supporting more batch sizes, so I add more images. We choose the context, we choose the data set for training, we choose the data set for the development. So once we are training, we can monitor our training, and we let it train. We're going to have a live demo after that. That's why I'm going pretty fast already. So here you see two charts, one on the right and one on the left. On the right side, you see the loss plot. So basically, what the loss means the error of optimization that we are doing. So what we want is to minimize the error. So basically, what we want to see is the numbers are going down. And on the left side, we see the dev and error feedback from the context. So we are predicting on the live on the train set and dev set, and we see how the train context is working. We also choose the best train during the epochs, so you don't need to be worried about problems like overfitting. For example, here the current epoch is 14, but the best epoch that we have chosen it's 13 based on the values that we have seen during the training. Since we are looking mainly for the numbers between 90 to 100 or 95 to 100, we can switch to the logarithmic scale. So it helps us to have a better visualization for those range of numbers. So if we, because the training takes time, we just clip it here and we go to the next video. After the training is done, what we want to see is that the error is starting high and then it's going slowly to the place that we are expecting. Once we have trained, we have our test set that we want to test if it's doing well or not. We predict on the test set, which the training had during the training we haven't seen that. We predict on the test set by the trained context, and then it gives us some visualizations of the results, so we can easily and quickly understand how the context was trained. So we have the confusion metrics, you have the scores, the distribution of scores. So this scores what it means, for example, how many images are predicted with the score of 100%. So every time that you do one prediction, the context gives you its confidence score. So here we see like how the distribution is for the test set. So to just show you some more examples of deep learning tool that we have. For example, once you have different type of pastas and you want to classify them, the traditional tools are not a good choice because every time the pastas have a different pattern. So if you want to learn them by traditional method, it's going to be really complex. Therefore, we use our deep learning. So what we do, we learn different type of pastas and we go over images, and then we can predict what type of pasta we are looking at. The second example is the OCR, optical character reading. Here we also have images of the strings. What we do, we use Boolean analysis again to locate the characters, and then we extract these characters and we train a context or a model to be able to predict the letter that is written there. For example, here we have MI278, and the context is reading MI278, but if you look at the I score, it's 88%, so it means that the context is not that much confident about this prediction. And the reason is because I and 1 are looking very similar. So that's why we are looking for a lower score. So these were the two classification, and here what you're looking at is a segmentation scenario. So for example, you have a sheet of steel, and there could be defects possibly on the sheet. So one could be the peak defect and the other could be the scratch defect. What we are seeing here is that the deep learning tool has located the peak defect on the sheet, and it's saying roughly here you could find the defect that you are looking for. So the big difference is that here we are using deep learning to also locate the defects. One more example of our tool. The usage of our tools is once we want to do bin picking. What does it mean to have a bin picking? It means like you have a bin and you have different parts of objects, different parts and objects inside the bin, and you want a robot to go and pick the parts one by one and locate it and put it in the right position. What we need here is a 3D camera. So once you see in the image that there is a camera scanning the surface of the bin, and then there is a robot that, for example, here is using the suctioning to pick the object. To do that, we can scan one part and use that as a model. So what we see in the middle, we have defined the part model, the 3D model of the part. And then on the right side, we are looking on the scan of the bin, and we look for this model inside that captured the scan of the bin. And we are choosing, for example, here, the best choice for us is the object on the top, because it's closest to the camera. And then once the robot wants to pick it, it's basically the easiest one. So that was an example of 3D analysis that we have. Back to there for the how to meet the high accuracy.
So, hopefully you found kind of these examples a little convincing. I think what's important about all of them is that we're not using purely machine learning to solve a lot of these problems. Deep learning, as you saw, is part of the solution to some of these problems, but typically we're combining it with our library with classical machine vision techniques. And the reason that you might want to do that is because you want to meet these high accuracy and performance requirements that customers often has. As you've seen, a lot of the time it's like in a factory setting where you've got that bin picking robot that wants to come find parts and move it into bins. And so you want to be able to do that, accurately and quickly. And so how do we actually develop code that does that? So the idea will be to give you a bit of insight into how we actually do this work. So I think it's important to remember that vision is only one part of the process, right? You first have to find a part somewhere in your image, but you then need to control a robot, like in bin picking, to come grab that part and then do something with it, right? Like assemble, put it together, move it. And the important thing to realize is that, since vision is only part of this whole long thing, and that robots move a whole lot slower than our algorithms can compute features, oftentimes the place we save time is in the vision bit. That's an algorithmic computer thing. We can crunch that time nice and down. And the less time it takes to find the part, The more time there is for a robot to do something, the more time there is to process another part, that sort of thing. So it's important to remind yourself that vision's only part of the process. And so performance is a real design constraint for MIL. So on the left, we have a really classic barcode reading example. Barcodes are everywhere in vision. People love reading barcodes. And you can see as we're running, this is a non-optimized version of our library. And it reads the barcode in 17 milliseconds, 12 milliseconds, 13 milliseconds, depending on the orientation. So the thing about that is that we can actually do a whole lot better by bringing optimizations into the system and actually optimizing our code and making it more performant. So with optimizations, we can rinse and repeat the exact same example, only now you have performance on the order of 2 milliseconds, 3 milliseconds, 2.2 milliseconds. So, you may say as a user, well, my cell phone can read a barcode, I don't care if it takes 13 milliseconds. And for an end user, maybe as a consumer, that's true. But in a production line where vision's only part of the process and you have to do a lot of different things, that's 10 milliseconds that you could be doing something else. So you could be doing some other algorithm calculation, you could be controlling the robot, whatever. And so a lot of effort goes into optimizing a lot of this code to take things from the 15 millisecond average down to the 2 millisecond average. And we have functions that frequently run in the microsecond range. And I think that's something that people aren't really aware of on general purpose computers. Another thing to realize is that a lot of the operations involve really complex arithmetic things to do, right? So finding closed edges, for example. You want to find all the closed edges in this image to see if the rubber ring is broken or not. Well, how would you do that? You would do differential operators, right? You need some sort of derivative math here to be able to identify that. Similarly, you have the exact same thing in machine learning, right? Gradient descent, right? You can't get away from differential operators. And then at the end, once you apply these differential operators, you get out these rings, and we can count all the ones that are closed, and we can exclude the one that's damaged. That's great. But you have to do a lot of floating point arithmetic to be able to compute all these features. Another constraint that I think people aren't aware of is that in reality, a lot of deep learning needs to be performed locally. So customers have industrial computers that are mounted in a factory somewhere. So this is one of ours, our Foresight. You'll see that it's a big hardened metal box. It's got no fans. It's got this big heat sink on it. Often these boxes don't have GPUs in them. They're CPU only. They have a lot of special I/O to control robots. And oftentimes these things are networked, but they're not connected to the internet, if they're even networked. And so the cloud is not really available to perform a bunch of deep learning. It's not like your Google Home where you yell at it and it does all this natural language understanding, but if you have no internet access, it doesn't work. In our case, this stuff has to work locally. And so that's true for both the classic stuff and deep learning. So that's a unique challenge, I think. So what we do is we have to create an industrialized version of our algorithms. That's key to providing something useful for a customer. So we do a lot of work in research and prototyping as a starting point, where you get something functional that actually works, right? And then from there, we do a lot of strategies to try and improve the performance and look at trade-offs in terms of time and accuracy. So there's really heuristics that are applied to try and make things more efficient, try and make things faster, while still being robust and accurate. And so this is kind of what real design processes look like in industry. And so for us, optimizations are essential for high performance. That's how we get those millisecond timings. So how do we actually do that? Well, one is that our library is developed in C++, C++. So a lot of people today will be prototyping in Python. When people think machine learning, they think Python, and that's great for prototyping. But at the end of the day, the actual algorithms themselves, to be performant, have to be written in C++ from our perspective. Similarly, our algorithms use multi-core, multi-process, so they leverage all the special features of the CPU they can. If you have 8 cores, we use all 8 cores. We really try and leverage the power of these computers. And we use all these special features that the CPU exposes, so things like AVX, SSE, MMX, all the sort of features that you would want to be able to improve and enhance the performance of these codes. So how do we do that? Well, we use these things called intrinsics, something you'll never really see in school, but you've seen sort of. So intrinsics allowed for these tailored behaviors. So they work on compiler built-ins. So the idea is that you can write regular C, C++ code and compile it normally, but that you're able to leverage the special CPU features like MMX, SSE. These are multimedia instructions that were typically used for video, but we're going to use them to improve our algorithms. And it provides assembly-like functionality, but in C++ directly for us, so we don't have to write assembly code. And so what are intrinsics? Well, they're portable and maintainable, unlike assembly. So you can do something like this, where this is a really common operation you want to do in any kind of algorithm. You multiply and accumulate. So let's say you have an array of 8 floating point numbers, and you want to take these 2 arrays of floating point numbers, and you want to multiply them together and add them, and then store the result in another array with 8 floating points. Well, you can do that classically in C with a for loop here with 8 iterations, right? And you can do all your operations. But that's going to be very intense CPU rise. You have at least 8 cycles because you have a for loop that goes around 8 times. Or you can use some intrinsics that provide this kind of functionality. So this is an intrinsic called M256. It supports multiply and add. And the M256 type takes an array of 8 floats, and it multiplies and accumulates them. Only it does it with 3 AVX instructions. So you've taken something that at minimum is 8 cycles and turned it into 3 cycles. And that really is how we crank out those improvements and get things down from the second domain or the millisecond domain into the microsecond domain. We use intrinsics to do these sorts of things. And the cool thing is that it supports multiple operating systems and CPUs, so we don't have to hand write all this assembly for all these different chips. So just to recap, we looked a bit at machine vision and how it automates inspection, kind of the product that we make. We talked about how you can combine deep learning and regular classical machine vision techniques to create really robust classifiers. They're both accurate and performant. We highlighted the fact that all this stuff really involves complex arithmetic operations, and that you really need to think about how you optimize that for industry and how you make it performant and robust, when you don't have cloud computing and when everything has to be done locally. And so that's that. That's what we have to say today. Does anyone have any questions? We are also open to questions about Mill in general, or about the challenge even a little. I see some of the challenge mentors are here today. We also have our software available if you want to see a little demo of something. Please let us know. So I quickly click on messages here. Cool.
I'll just, excuse me, I'll just say, if there are no questions, feel free to ask a question if you have one. If you could do a demo just for the recording, that would be terrific.
Sure. So, we showed a bit in the video how you can actually go about doing a lot of this stuff. But I thought maybe it would be cuter to see an actual demo of our software that we use to do a lot of this. By chance, can everyone see that?
I can see.
Yes.
Excellent. So this is CoPilot. So it comes with Mill. So we provide in the challenge instructions how to get Mill and install it and activate the trial version. So if you have questions about how to do that, feel free to ask. We're around to help you set that up. So this is the graphical user interface, CoPilot, that we use to help prototype things with the library. And so I thought I would do a little example of doing a deep learning model with CoPilot. So you can think of CoPilot kind of as like an IDE. It kind of helps you use our library. So we support a ton of stuff, but we're going to focus on coming to analysis here and doing something with image classification. So I have some images on my disk that represent different kinds of fabrics, and I want to be able to build a classifier that will identify those fabrics. So I need data sets to do that. I need labeled images to be able to do that. So I can come here and create a data set, and I can add images to them and label them. So I'm going to go ahead and do that. So I'm going to edit my data set. I'm going to add some images. I happen to have some images lying around of these fabrics. So let's come here, classification, fabrics. And I have these 3 different fabrics. So I'm going to open this folder of all these fabrics. So you'll see here, these are all these fabrics. And I want to label them. So I'm going to define some labels. I happen to know there are 3 kinds of fabrics. So I'm going to say, well, I want fabrics 1, and I want fabrics 2, and fabrics 3. And they've been given different colors to tell you that, oh, this all represents fabrics 1, this represents fabrics 2. So all these fabrics here happen to represent fabric 1, so I can come around and manually label them up. This is fabric 1, this is fabric 1, etc. Luckily, I know everything in this folder is fabric 1, so I'm just going to select them all and say they're fabric 1. I can do the same thing by coming back up here after I've defined my labels and say, you know, all these new images I'm going to add, they represent fabrics 2. And that's great because my data is already cut up into folders that's kind of labeled, if you like. So I'm going to say, let's build all of fabrics 2. I can come here and I can build all of fabrics 3. And I now have a data set with all these different fabrics labeled. Well, I can see there's all fabrics 1, there's all fabrics 2. They look a bit different, right? And there's all fabrics 3. These are all the kinds of problems that are very hard to solve with classic machine vision, because as you can see, the fabrics look different to a human, but they don't have a lot of interesting geometric features to kind of distinguish with regular machine vision. So once I have this, I have a data set that's prepared to do machine learning with. Instead of going from scratch here, you need another data set that's open with you need a train and a dev data set. So we actually have all that pre-prepared. So I'm going to go ahead and open that so you can see that demo. You have all these demos. It's the class CNN complete train. Oh yeah, because I have that one. Okay, well fine. I guess I will do it by hand. Jeez. Let me bring this back. That's what happens when you try to do demos, right guys? Okay. So I digress. Let's try this again. Okay. Fabrics 1, fabrics 2, fabrics 3. I'm going to add my images. Here's all of fabrics 1 again. Here's all of fabrics 2. And then here's all of fabrics 3. Great. So now I have a data set you can see with all the images here labeled, and there are about 600 entries. But I need both a trained data set and a dev data set. So I'm going to take this guy and I'm going to split it into 2 new data sets where I can decide what the percentage is. So I don't know, what's a reasonable percentage? 20%, Benham, does that sound reasonable?
Yeah,
it's like
you can go for it. It's going to give you 20 and 80, or if you put 80, it's going to give you 80 and 20.
Okay, well, so we'll do that. So we're going to split it this way. So now I have 2 new data sets, one that has 120 entries and one that has 480 entries. So we're going to call the bigger one the train data set, and we're going to make the smaller one the dev data set in this instance. Dev data set, as people watch me type, very scary. So now I have my data sets. So now I can actually start training a classifier to be able to recognize these different fabrics. So the way you do that is you come up to analysis objects, come back to the classification module, and now you need a training context. You can think of it as the container that has all your settings for doing training. And you can see all the different settings up here, like the mini batch size, the max epoch, but usually we pick defaults that are pretty decent. The other thing you need is you need an architecture to begin training with. So we provide all these pre-canned classifiers that aren't trained, but that are of a certain architecture and a certain size and support certain images of certain shapes and sizes. So I'll pick FCNet medium, for instance, and you'll see here it's untrained, and it takes training image sizes that are like 8-bit unsigned, and they're A3 times a factor of 8 by a certain size, right? So they take a certain size. So that's just something you need to get started. So then once I have that, I really can actually begin training. So I can, right here in the user interface, I can hit train. I pick a classifier, my FCNet medium, the architecture I want to start from. And then I pick my train data set and my dev data set. And then the results will be stored here on disk. This is the actual classifier, and these are the 2 resulting data sets. And I hit OK. And now the training will begin on my system. And you'll see here, it'll start training. So we see the loss function rolling around. And then on the left, we see the train and dev error rates as a function of the epochs, so as they go along. You can see here that, sometimes we spike up, sometimes we spike down. But as Benan pointed out, we only update the model for the best epoch that was last done. So we actually had a really good epoch at like 25, where we can look at the log axis here and see that, we're really, really low in the error rate. I don't even have to let the training finish. I can hit stop. It's probably good enough. So then the training stops. We patiently wait for it to finish saving all of the results. Excuse me. Here we go, it's getting there. Cool. So now that the training is finished, we actually have our trained context here. So here is our trained context. So what does it do? Well, it expects images of size 131 by 131. It is a fully trained network that follows our FCNet medium architecture. And it can predict 3 types of fabrics, where the first result represents fabrics 1, and the second is fabrics 2, and the third is fabrics 3. And now we can actually take this and do prediction on some data. So what I'm going to do is something you shouldn't do, which is take one of my existing data sets and predict on it. Clearly, it will be 100%. It was used in the training. But, you're supposed to have images on the side that you saved to do this kind of work. So I can take this dev set here, and I can actually predict on it. So now it's predicting these various images off the disk, and it tells you how good it was at guessing this. So the very first one, it said, well, it's likely fabric 0 with a 99.58% confidence. And what image is that? Well, that's this image on disk. And it did it for all of them. And you can see here broken down by class how many classes it got. And this, so now, once you have this classifier in hand, you can actually use it to do prediction on images. And so this is kind of how you do deep learning, essentially in a very simplified way, once your images have been both labeled and cut up and preferably augmented and all these sorts of things. This is how you can actually go ahead and use our software to do a lot of this stuff. We talked a little bit earlier in the last presentation and in this about how you augment images. And so it's important to realize that, we only have like, 100 and so entries here. Well, that might not be enough images for your classifier to be good at recognizing something. So oftentimes, we use augmentation to improve, sort of the robustness of the classifier by giving it more examples of each type of fabric or each type of class you want to do. So in this case, I can take this image and maybe I could blur it a bit because that represents like a camera being out of focus. Or I could add noise because maybe that's something realistic that happens in your example. So what we'll do is I'll quickly show you how you can actually do that with our library too, because all that functionality is pre-canned. So I have my image here that I want to augment. And I can come up here to the processing objects, and I can allocate this thing called a new augmentation context, which helps you augment images. And with this, you can select the type of augmentations you want to do. So you have to know in advance kind of what kind of augmentations are realistic for your application. But I think blurring is usually pretty common. So what we're going to do is I'm going to find some blurring here, some smoothing, and we're going to enable some smoothing here so that we get some blur that will happen on your images, some smoothing. So what's going to happen is this thing will, in a random way, pick a blur factor to apply to the image that you give it. And you can do that over a whole bunch of images. And what it will do is it will randomly choose a blur value, and it will also randomly choose between the different augmentations that you've selected and apply them to the images. So I'm going to pick my image here, and I'm going to pick this cute image. And you can see a little preview result here. It got smoothed out. But it might not always get smoothed out the same way. So what I can do here is I can hit OK. And now it's generated for me 5 new images, because I asked it to do it 5 times, of that same original image, only blurred in slightly different ways each time. So there's one, there's another one, you know. And the interesting bit about that, of course, is that you now know, well, these were all Fabric 1. So you can put them back in your data set and say, hey, here are more Fabric 1 examples. And now you have more images to do your training with. And so this is a way that you can kind of control that sort of thing. And you can do other crazy things like salt and pepper noise is pretty cool. You can turn salt and pepper noise on. And when you look at the resulting image, let me find the image. You'll see here that now it's not only blurred, but there's also all this salt and pepper black and white noise. That's like a common thing that we see with cameras sometimes. And so you can use our tool and our library to kind of do these kind of vision activities. I mean, the library does a lot more, and so does the UI. We have tons of processing features I'm not going to go into. But I think those are the real two that you kind of want to have a look at for doing deep learning. We have a really involved and big help system that you can get from Control Center. So if you look at the mill help, though I clearly have the internal version. In the user guide, I posted links as well in the challenges channel to the online version of this. There's a whole chapter on classification that goes into all the steps to do this, how you build a data set, how you do training, how you do prediction, how you do things like augmentation, course segmentation, all these more sophisticated things. And there's also a section on, I think it's in fundamentals, on augmentation somewhere. Oh, I found it this morning. Anyway, I put the link inside the, it's under specialized, specialized augmentation. Here's a whole section explaining how to do augmentation as well. And so I put those specific links to augmentation classification in the challenges channel for those people who want to find a bit more information and learn how to do this stuff. We had some interesting questions last night about this, about whether you could use this to do some of the other challenges that had like a bit of a machine learning twist. Feel free to use our software to do whatever you want. You can process any kind of images with it, as long as you're doing like image classification. Clearly, our system doesn't help you do like natural language understanding, right? It's not going to help you do audio or something. We do vision, but feel free to play with our product and use it to do whatever you need to do for your challenges this weekend. Now that I've shown that, are there any questions? Okay, well, I'm guessing not. So I hope you've all found this useful and interesting. Mentors will be available, I believe, at least in the morning. Yeah, I can see there are people there now. In the Matrox lobby to give you a hand with some of the stuff. Feel free to ping us and ask questions. We're going to be here to support you a bit. And of course, feel free to refer to these videos so you can kind of have a look and see what we're talking about. Yes.
Thank you, guys. We really appreciate you taking the time this morning to give this workshop.